Okay, year 12, question 11. Right, this was tricky, and it did involve a little bit of thinking, what's going on here? Like I said, a completely different scenario than to what you're probably used to. But it's about experiment to determine the internal resistance of a power supply. What we should know internal resistance. We should know the core practical to find it. But this has got 4 resistors. Why has it got 4 resistors? I've not seen this before. Well, we're varying the load. Okay, we're varying the load by doing different combinations of 2 resistors. So it's using different areas of knowledge of electric circuits in one question. So this is why your core knowledge and understanding of a whole throughout the whole topic needs to be, recalled, as quickly as possible. It needs to be permanently there. Yeah, you can't be sat here thinking, "Oh, how do I calculate combined resistance of 2 resistors again?" Or you can't be thinking, "Oh, what's the equation? What's the equation for internal resistance again?" Your knowledge, understanding has to be right, bang up to date. Okay, right. So what do we got here? It's determine the internal resistance of the power supply. We've got 4 resistors. I've not seen this before. Right, 4 resistors. The student can change the load, the external resistance R, between X and Y. Now, it does it by having 2 resistors in series or parallel. Right, you can get 12 different values of resistance. Mathematicians might know that. Right, calculate the largest. Right, which combination, series or parallel, is going to give us the largest resistance? Well, you should know that when resistors are in series, you add them together. That's what gives us the biggest resistance. And the biggest resistance is going to be the biggest individual resistances. So 6.8 plus 8.2. Okay, so 6.8 plus 8.2 equals, 15 ohms, isn't it? All right. Okay, I wasn't checking there. I wasn't looking to see what I'd written down. I did know that. I'm just getting my page. Right, what about the smallest? Okay, about the smallest resistance. Smallest resistance, well, it must be in parallel. You must know that if you have 2 identical resistors in parallel, the effective resistance is half of the individual resistance. Okay, so adding resistors in parallel makes the overall resistance drop. Okay, now which is going to give us the smallest in parallel? Well, it's going to be the 2 smallest, isn't it? Right, so 2.2 and 3.9. Now the equation is 1 over RT is 1 over 2.2 plus 1 over 3.9. Okay, that's correct, isn't it? 2.2, 3.9. Yeah, that gives us an RT of 1.4 ohms. Easy peasy. Right. With the switch closed in the on position and no resistors between X and Y, okay, with the switch closed and no resistors connected, the voltmeter reading is 1.62. Right, so if we have just a voltmeter, no resistors, because voltmeters have a very high or almost infinite resistance, there will be no current flowing. Right, this is the key idea with internal resistance and lost volts. If no current flows, then no volts are lost in the battery. Because if no current flows, then no energy is lost. So if no current flows, the voltmeter will be reading the EMF of the cell or the battery or the power supply. Okay, so there's your answer there. No current flows, right? And the reason why no current flows is because the voltmeter has a very high resistance. Right, this is a particular combination. We've got the 2.2 and the 6.8. Right, the voltmeter drops to 1.14. Explain. Right, again, it's because now a current does flow. Okay, now if a current does flow, then current will flow through the battery. if current flows through the battery, energy will be lost due to heating up in the battery. That's what the internal resistance is. Okay? If energy is lost there, there'll be lost volts across the internal resistance. Because some of the energy, not all of the energy, goes to the load. Because some is lost in the internal resistance. Okay? So again, this really should be you guys not thinking about it. You know, your understanding of internal resistance and lost volts and what EMF is really should be, you know, you should be saying it in your sleep, basically. Well, not that far. Right, here we go. So we want the value of R, don't we? So what values have we got? We've got, well, from the early part of the question, yeah, EMF was 1.62, wasn't it? So 1.62 volts. Right. The voltage across the external load, 1.14 volts. Okay. The value of the external load. Okay. Actually, right. What else? With the value of the external load, if the value of the external load is, what have we got? These are two, they're in parallel, sorry, they're in series. So 2.2 plus 6.8 is 9, isn't it? So the external load is 9 ohms, and the voltage across the external load is 1.14. We can calculate the current, can't we? Okay, V equals IR. So I is V over R, isn't it? Okay, so 1.14 divided by 9 is 127 amps. Okay, so that's the current that flows. Right, so we now know I, we now know V, we now know E. We should be able to get the internal resistance. Right, the most commonly used internal resistance equation is E equals I small r. That's the voltage drop across the internal resistance plus the voltage dropped across the external load. That's my favourite version of the most common equation, because that just comes from conservation of energy in that form. So what values have we got? We've got 1.62 equals 0.127 times R. Don't need the brackets. Okay. In fact, I'm going to put the little r closer. There you go. Plus 1.4. 1.14, that's the voltage across the external load. That gives us an internal resistance of 3.78 ohms. Okay? That, I believe, is a very straightforward internal resistance question. It's just complicated by the fact that your external load comes from two resistors in series or parallel. Okay? But that is as straightforward as internal resistance gets in a question. Okay, right, question 12. It's catapult, isn't it? Right, what's going on here? We've got something balanced. Oh, it says pivot, it says pivot, it says pivot. Yes, it says pivot. It's got to be a moments question. Okay, right, moments, yes. We've got tension in the rope. Yes, it's got to be a moments question, hasn't it? Right, there's the pivot. Now, it's an old-fashioned catapult from medieval times. Well, the counterweight is a wooden box full of stones attached to one end. The projectile is a large rock. It's in a sling and it hangs vertically from the end. Right, we've got a rope that stops it being fired. Okay, when they want to fire it, they cut the rope, and the counterweight produces a bigger clockwise moment, which flings the projectile, the rock, up in the air. Okay? Genius. Right. It's designed that when the counterweight wooden box and the sling are empty, there's no tension in the rope. How does the pivot position achieve this? Center of mass. Okay, you should be like saying, okay, when this and this are empty, the center of mass of the wooden beam, the sling, and the box must be here. Okay? When the sling and the wooden box are empty, the center of mass of the whole thing is directly or vertically above the pivot. So, if the center of mass is vertically above the pivot, there will be no or zero moment on the catapult. Okay? Or the total clockwise will equal the total anti-clockwise. That's what you need to say there. Right, stones. Okay, I've got a mass of 610 kilograms. Right, and the projectile weighs 250 newtons. Ooh, it's given us weights and masses there. Yeah, who fell for that? Anyone? Okay, let's have a look. This is where we can go back to our diagram. This is where we can annotate it. That will come in very useful, I think. Right, let's annotate. Orange, red, no, red's nicer. What have we got? So we need to draw the forces now, don't we? We've got the stones and the counterweight. Right, we can ignore the mass of the box. We can ignore the mass of the beam. We can ignore the mass of the empty sling because we already know that the combined weight of those things produces a centre of mass vertically above the pivot. The only things we need to consider now are the stones we add to the box and the projectile that we add to the sling and the tension in the rope. Okay, so that's what we need to draw and add to our diagram. So let's go with the stones in the box. How much have we got added? Okay, well, that's mg, isn't it? So that's going to be, it's telling us that, how many stones? 610 kilograms. So we've got 610 kilograms times 9.81. That's producing a weight or force downwards there of 5984 newtons. What else have we got? We've got the weight of the projectile going vertically downwards there. Now it gives us that. We don't need to do mg. It actually gives us 250 newtons, which is nice of them, isn't it? There you go, 250 newtons. And then we've got a final force. We have got a final force at an angle here, T. That's at an angle 50. Okay, it's at an angle 50. So what I'm going to do here is resolve. It'd be really useful to find the vertical component. Ignore the horizontal component. Why? Because that goes through the pivot, doesn't it? This component of tension there goes through the pivot, so that's not going to produce a moment. See ya. Right, the vertical component is important. Well, what's the vertical component? Now, it's all upside down, isn't it? It's either t cos theta or t sine theta, theta being 50 degrees. So it's either t sine 50 or t cos 50. Well, there's 50 there. So it's the horizontal that will be cos, because that's adjacent to the angle. The horizontal component of t will be the cos one, because that is adjacent to the 50 degrees. So it's sine, isn't it? So we've got t sine 50 degrees is the vertical component down of the tension. Right, we've got two forces now. T sine 50 and 250 vertically downwards from this position here. And we've got 5984 newtons vertically downwards from this position here. We now have a moments calculation, don't we, to find T. Okay, we can just add together that and multiply it by the perpendicular distance, 4 meters. That's going to be equal to that multiplied by that perpendicular distance. Okay? Should be fairly straightforward from here on in. We've got, what do we got? We've got t sine 50 plus 250 multiplied by 1.5. That's the anti-clockwise moment. That's equal to the clockwise moment, which is 5984 multiplied by 1.5. I meant to write 4.9. Okay, so the perpendicular distance of the left-hand side is 4 meters, perpendicular distance of the right is 1.5. That should give us a tension of 2603 newtons. Okay? Right, say, oh, hang on a minute, it was a moment's question. What's going on? It's now projectiles. Yes, come on, you got to get used to mixing it up within questions. Right, so it's a projectiles question now. Yeah, it's launched vertically. So it's launched horizontally when the catapult gets vertical like that. So it's a fairly straightforward projectiles question here. So what do we do with projectiles questions? Of course we do. We need to split down the middle, and we're going to go vertical first and then horizontal. Right, what do we got? So vertically, initial is 0. Let's take downwards as positive. So A is 9.81. It's going to move vertically downwards, a distance of 7.5 meters. I'm going to use S equals UT plus a half AT squared, but because U is 0, it's a half AT squared. Okay, S is 7.5, A is 9.81. That gives us a value of time to be 1.24 seconds. So it takes 1.24 seconds to fall vertically from here to here. So if it takes 1.24 seconds to fall vertically from here to here, it takes 1.24 seconds to move horizontally from here to here. Okay, that's what projectiles questions is all about. So going over, we've got an initial horizontal velocity of 18 meters a second, but because there's no air resistance, that stays constant. The time is 1.24 seconds, so the horizontal distance is 22.3 meters. Okay, so there's your horizontal range. Really straightforward projectiles question there. Okay, now finally, part D, it's saying, what if it's launched not horizontally, but what if it's released before it gets vertical? If it's released before it gets vertical, it's going to fly off at an angle. Right, interesting question this. There's no right or wrong answer, because obviously we need more details. We need to know what speed it's projected at, what angle it's projected at, before we could categorically say whether it goes further or not as far. Okay, so you could go down either route. Okay, you could argue, well, if it's launched vertically upwards, it's going to have a vertical component initially upwards. It's going to spend longer in the air. So if it's going to spend longer in the air, it's going to travel further horizontal distance. Conversely, you could argue, well, if it's going to be released before it's vertical, then the counterweight is going to drop by a smaller height. So there's going to be less energy to start with. So this initial velocity might be V. Okay, so there's two different directions you could go down there. Anyway, that's questions 11 and 12. Thank you.